Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate SVI index or a standardized vegetation index. The SVI is one of the useful indices for drought monitoring based on vegetation dynamics. At the end of this tutorial, you will be able to calculate the SVI with annual frequency for your study area that shows how vegetation situation changes regarding to the drought situation. So this tutorial is really useful for those of you who are interested to study about the drought monitoring using Earth observation satellite data in the Google Earth Engine. If you want to learn how to do this procedure from scratch, let's follow this tutorial. Make a new notebook, and first step, we need to import necessary libraries to deal with the Google Earth Engine facilities in the Colab environment. So, start with EE and GEE map library. Remember to install the XEE library. As I mentioned in the previous tutorials, the XEE is one of the newest libraries developed by the Google community and allowing us to combine the Xarray format with the Google Earth Engine format dataset. It's really useful because thanks to the XEE and Xarray, we will be able to use Python machine learning algorithm on the dataset available in the Google Earth Engine platform. So the next library should be Xarray. Xarray has XR imported. Let's run the cell, and after a few moments, the library is settled and we can go to the next step. Once you saw this message successfully installed, then you can clear the output messages. So now we need to establish a connection between Earth Engine and Colab environment. Authenticate first and then initialize your Earth Engine account. Let's enter the project ID. Go to the code editor environment, this address, code.earthengine.google.com. If you have already an account here, upper right here, there is an icon. You can go to the project info and find the project ID. So, copy and paste it into the code, just like that. The next argument is the OPT URL. So, if you search on the net about the Xarray library and Google Earth Engine, you will find a GitHub page, this address, a detailed instruction about the XE, and there you can find the OPT URL address. There you go. So, now I'm trying to copy and add it into the code. Let's run the cell, and Colab asking you permission to access to your Earth Engine account. Click on Allow. Then select the associated account connected to your Earth Engine account. Click on Continue and Continue. After a few moments, we have access to the Earth Engine resources in the Colab environment. So now we need to set the region of interest in the first step before further analysis. Create a variable map called the GEE map and bring the map function with a satellite base map, just like this. Let's run again. After a few moments, you will have a user interface. With some drawing tools, you will be able to find out your region of interest. Originally, I'm Iranian, so I prefer to choose my study area from my own country. This study is based on the vegetation cover, and drought monitoring is based on the vegetation situation. That's why I prefer to select an area with a dense vegetation cover in the northern Iran. So here we have Gilan province in the north of Iran. So I need to select this area as my case study. In the next step, I need to use the FAO administrative borders to find the administrative border for this province. So make a new cell. In the Google Earth Engine, FAO administrative layer is available. There you can copy and paste the feature collection. So, but before that, we need to actually convert the drawed region or this point to a shapefile. So make a new variable, point sets to, and then from the map, draw last feature, convert it into a geometry. As you can see, point now available as a shapefile. So now we can filter our province based on intersect with a point. It's really easy to do. Just we need a new variable for the file data set. The ROI sets to paste the feature collection belongs to the file, and then make a spatial filter or filter bounds based on intersection with point or based on overlap with the point. So finally, we can have the Gillan province as a geometry while it is simplified with 1000 degree. Let's run the ROI, and now the image collection, the geometry created. If you want to make sure the study area selected successfully, you can plot it on the map. It's very easy to do. Map.addLayer is a function to handle this process. ROI, then ROI again. After a few moments, you can see the shapefile for the selected province. So, region of interest selected without any challenge. In the next step, we need to call the vegetation product. In this tutorial, I prefer to use the VIRS tutorial. VIRS is a complementary satellite for the MODIS data. Actually, it's launched and started missions since 2013, and the NASA planned to use the VIRS data as a mission that continues the MODIS project in the future. So, as you can see, it's dataset available since 2012, not 2013. It was my mistake. So, image collection snippet available here. I'm using vegetation indices 16 days, 500 meter. But the question is, why VIRS is a complementary for the MODIS? Because the band's characteristic, spatial resolution, and temporal frequency, everything matched with the MODIS, and whenever the MODIS fails, the VIRS can be a good replace or an alternative that continues MODIS missions. So, feature collection is available here, and now the collection ID actually copy from there. You can copy the image collection from there and bring it into the code. So here I have a data set for EVI, make a tuple and paste the image snippet, make a temporal filter. For example, I want to use the 10 years data from 2015 to 2024 until 2025 because 2025 not included. So, and as you can see in this product, we have several bands, vegetation related indices such as NDVI, EVI, and also surface reflectance values. But I prefer to use the EVI for this tutorial. So typically people use the EVI for SVI index. It's also another powerful vegetation index complementary with the NDVI, and we can use it to see more anomalies and more information about the vegetation cover. So select the EVI just like this. Let's run to see how many EVI image available over the 10 years. It's actually 16 days frequency, about 460 elements available throughout the time. And in each date we have an EVI and also the temporal and also the properties or the metadata information available with the EVI dataset. And there is no scale factor for this dataset, so we can use it as like it is. Just remember to clip it based on the region of interest, because our region of interest is a shapefile polygon, and we need to and make sure that the region of it, that the data set, the EVI data set clipped based on a border. Make a loop structure through the map to do this process. So lambda is a temporary function. Each input considered as an X that is clipped based on a ROI. Finally, I need to make sure the new output, including the system time start information or data acquisition information from existing property in the data sets. So system time start and existing property already called by X. Let's run again. And after a few moments, you will see only one property is available here, but I hope it works. System time start should be available, and it is. Yeah, there is no problem. So we can go to the next step. In the next step, we need to convert the EVI to an Xarray format. So let me make a new cell because I want to compare the Google Earth Engine format or image collection format and Xarray format. It is easier to understand what's going on after doing this conversion. As you saw earlier, we have an image collection format in which we have a collection of data and also some features, all of them listing into a single collection. We have bands and also the properties, just like that. But now we want to convert the image collection format into the Xarray structure. Because in image collection format, we're not able to apply the machine learning algorithm in a Python on this data set. So it is important to convert it into the Xarray format. So from XR, let's open the data set. The input is EVI, engine sets to EE, CRS, EPSG 4326. This is WGS84. That's the unique ID that's used for all around the world. And the next is the geometry or region of interest set to the ROI. The scale size is open. So the scale is important here because the coordinate system is based on a geographical coordinate system. So a scale is based on a degree. 1 degree, 100 kilometer, 0.1, 10 kilometer, 0.01, 1 kilometer. I want to actually resample the data set from 500 meter to 1 kilometer because in the province scales, there is no much differences between 500 meters and 1 kilometer, at least in this step. But the benefit in 1 kilometer is that I can increase the speed of processing and it is easier to handle this data. So let's run a data set and see what's happening there. But something's wrong here. Yes, the argument engine was wrong. There was a typo here. Let's run a cell. After a few moments, you can see the data set is ready. Now I'm printing the data set and you can see a multidimensional structure here. We have a variable named EVI. Its value available over time, longitude, and latitude. So here we have a three-dimensional data. One dimension is time and another one is longitude and latitude. So in the next step, I want to show you a trick in the Colab environment that helps you to increase the speed of processing. Whenever you do this conversion from an image collection into Xarray format, it is necessary to sort your data based on the temporal frequency. The DS sort by time, just like this. But here, if you do a simple calculation, very simple, that doesn't change the values, for example, by multiply to 1, in that case, you will have a new data set separated from the initial one that it works much faster from the initial data set. So scientifically, there is no reason behind multiply to 1 and nothing will be changed after that. Just we will have a new data set separated from the initial data set. I don't know why, but it's really helpful to increase the speed of processing. So let's run a data set. And now we are waiting for sorting and multiplication. Once the process is done right now, we can go to the next step. So in the first step, as you can see in the previous example here, first of all, I want to actually calculate the SVI index. That is really important. To calculate the SVI, we need to apply this relationship. Each EVI band minus to long-term average over to long-term standard deviation. So that's the equation. To do this, we need to calculate the average EVI. So the ds min sets to ds.min over temporal dimension. Let's do this for a standard deviation. ds.std, just like that, over temporal dimension. So the average and standard deviation calculated. The next step is SVI index. Make a parenthesis like this, ds. Each EVI image or data in the ds minus subtracted from the average divided into a standard deviation, just like this. Now the SVI is ready and we can use it for the further analysis. So if you want to do a visualization, it is easier to actually convert it into the annual format and compare the annual SVI conditions. So SVI annual sets to get the SVI and use the resample function, convert it into the annual format. For each year, I want to have the average value through the time. SVI annual now calculated. There you go. You will have 10 SVI bands through the time. Let's do the visualization. It's really easy. Just we need to select a variable that is the EVI and make a plot. The plot has different axes. X-axis sets to the longitude, Y-axis sets to the latitude, call axis temporal dimension, and the next argument is called wrap. I want to have 5 map in each row in the plotting process, and the color map should be, for example, the color palette could be, for example, turbo R is my preferred color here, and robust, allowing us to have the highest contrast in the output. Okay, as you can see here, we have a multi-temporal plot that shows the average SVI index for each year. The band name is EVI, but the results are here the SVI index. Ranges from positive to negative values. The positive values showing that vegetations are healthier and the moisture is higher in the study area. And also the negative values or the red color showing vegetations or NDVI is not EVI values not good compared to the long-term average and a standard deviation, and also maybe we have a severe drought in that time. So as you can see here, some of the years, for example 2019, we have more blue colors, meaning that more positive values, specifically these areas were covered by very dense forest regions. So as you can see, or 2024 or 2023s, these are wet years, or we had more moisture compared to the rest of the years, specifically in 2017 and 2018. So that's another way, that's a way of interpretation for the result. And now if you want to get export from the result, it is very, very easy to do. Just before getting export, it is essential to call the matplotlib. import matplotlib.pyplot as plt. So it's essential for working with the plots. And now I'm gonna save the fig here, the SVI with annual format, get export as a PNG, DPI sets to 360 inches, and BB box inches here sets to tight to keep all the elements inside the figure. And also it is possible to change the format, the plot format into the contour style, but not necessarily, because the visualization is good and we can see the dynamics, spatio-temporal dynamics with a good quality. Let's run a cell, and after a few moments you will have the annual fig here in the left panel. Just go to the download. The dataset is ready to download in your system. So as you can see, the SVI annual with a good quality is available and you can have it in your report. So there you go. As you can see here, it has very good quality and we can use it for drought analysis in your study area. Or sometimes you may need to have the SVI values with 16 days temporal frequency, its average value over the area. That's another thing you may need to try for. So SVI annual, I want to get the average over spatial dimension over the region, get the SVI annual, calculate the average, this time over spatial dimension, longitude and latitude. So then I want to convert it into a data frame, SVI annual mean to data frame. So remember to drop the NA values, no datas. So at the end you will have SVI annual DF, a data frame with two actually, but this is for the annual format. I will show you how to do this for the 16 days data. But as you can see, we have two columns, one time and another the EVI. If you want to have it in the Excel file, it is really easy to do this using .2SV for CSV format. SVI annual .CSV, just like this. In the left panel, you can have the SVI annual with CSV format. You can bring it into the Excel for the further analysis. So that's another good example that helps you a lot to get understanding about the data. As I said, it is not EVI, just the band name is the EVI, but the values showing the SVI index. So back to the code, and now if you want to make a plot for SVI annual, it is also really easy. Just you need to do like this. Remember to select the variable name, that here it is the EVI, but the data frame, we should select the data frame and make a plot. You can see in the initial years from 2015 to 2018, the average for the study area was below zero, negative values showing that these are the very severe drought condition in the study area. But in after 2018, 2019 was a very wet years, because in there we can see the SVI values increased or raised a lot. And again, you can see some years we had a very different situations, sometimes more moisture, sometimes lower moisture, sometimes we had drought, sometimes we had wet situation. And 2014, 2024 also was another year with the wet condition, as it was already addressed in the visual comparison. So now we want to do the same process, this time for the data sets for the SVI, for a normal SVI with 16 days temporal frequency. So let's do this. Here we already have the SVI for 460 days, And here let's make an average from the SVI. Calculate the average over longitude and latitude. SVI mean converted into a data frame dot drop NA. SVI mean data frame. Now you can see we have the same number of the rows here in the data frame structure. You can save it into a CSV file using SVI min, but SVI 16 days this time. .csv, just like that. So now you can see it's available. You can download and bring it up into the Excel software. So in the next step also, I want to show you how to make a plot for SVI main data frame. Just paste the variable name and make a plot like this. You can see a seasonal variations. Sometimes we have wet times, and there we have more vegetations are healthier in some of the months because of the climatological situation and also the temperature. And sometimes the EVI values drops because the vegetations are not in a good situation because of the climatological situation and the growing season. And that totally makes sense. The annual for the 16 days format dynamically varies from positive to negative values. So, but it's important to actually see to the overall situation in the annual format. So maybe you want to get export for the or raster for the netcdf data set. You want to use it for the further analysis in the another Colab environment. It is also possible. Just we need to install netcdf format, netcdf4, to get export this data set from the Earth engine. So once the netcdf installed and imported here, the annual SVI is ready to export, just like this. This time .to netcdf SVI annual grid, for example, or annual array .nc format. Let's run. In the left panel, you can have access to the netcdf format too. The netcdf format is useful because you can actually save your data set and keep it for the further analysis in the GIS software or even in the new programming plan. So I hope you liked this tutorial as much as I did. If you faced with any challenge during this tutorial, the code example is available below this video on my YouTube channel. And if problems still exist, you can reach me out and put your comments there. And please share this tutorial with all remote sensing fans in all around the world. Thank you for your attention.